So no problem, then let us begin with this one. Angular version of Ceva's theorem, right? So, okay, so I will quickly write down the statement once again. So this is supposed to be a very simple statement, right? There is not, isn't supposed to be anything in this. So these are not midpoints or anything, it's arbitrary lines. C, D, F. Yes. So what should be the strategy? So we know what we have to prove, right? So we know that sine beta by and cyclic product, just move cyclically here and just take the products. Obviously here the main thing is that all these are these lines are meeting at this point. So what should be the strategy? Yeah, well, it's very simple. The point is, so Aparna, were you able to do this one? Well, see, the point is that you have to connect this ratio. You have to connect this ratio with, as you expect, right? BDDC, and it will also involve the two opposite sides, right? We even know the exact formula, what the connection is, but let's assume we kind of don't remember it. We still can derive it. This is the connection we have to make, right? To connect this with this thing. Obviously, eventually we are going to apply the usual Ceva's theorem. So what's the connection? Can just all of you try it now? It is this, right? This is actually equal to this. But do it yourself. Don't believe this. See, you people have to give time to the subject. Okay. This class is just 1 hour, but in our times we used to give, I mean, and now we even give more time because maths is all I do mostly, and means in my academic life. So, but yeah, you people have more subjects, but you have to find the time because then only you can get good. Any progress? So we have to, since all we know so far almost here in this kind of question is sine law, right? So why don't we just apply the sine law? So you can, right? So for this much, you can simply forget these things. And this just becomes a question in sine law. Yeah, do it. You have to do this one. This is, take ABD, apply sine law, take ADC, apply sine law. You should get it.
Sir, I got it actually.
You got this right? Okay. So can you say the way in which you got it?
Sir, first if you take triangle ABD, then you'll get that sine beta by BD equals to uh, the whole sine angle B and of angle ABC by AD.
Right. Yeah, so this is beta. 1 second. Sorry. Yes.
Sir, and then if you take triangle CAD, you'll get sine alpha by CD equals to sine of angle ACB whole angle C by AD, and then you divide both of them, you'll get the answer.
Uh, yes, that's actually a, in some way that's a better answer actually. So here I see something. So that's, we don't get exactly, means, okay, it's all same. So sine beta by sine alpha, right? This becomes, so I'm just writing it straight away. Okay, other things are getting cancelled. This is what you get, right? Okay, so this, hold on. So I wrote something wrong here. Yeah, so first thing is that this is wrong. This is CD by BD, right? Yes, it's a cross, right? You see, it's AB and yeah, and so this is completely wrong probably. This is the AC. How did I write BC? Sorry. Did I, was that the source of confusion for others? But if you compute, you should get the correct answer. Yeah. So kind of, right? This is AB and this is AC. And let's just work it out. So what we are getting is BD by CD, it's this. But then again from the sine law, we know that sine B by sine C is AC by AB. Is that right? Or is it, sorry, so AC,
It will be AB by AC.
AB by AC. Yes. Right. Yes, it is the cross. Yeah, you can see it in different ways. It is. Okay. So we get, okay. So there is absolutely nothing in this question, right? I mean, if you did not know sine law, then you may have to, okay, now we have to drop some perpendiculars and then do some trigonometry and some more. But now you already know the pre-made thing, so there's nothing to do. Okay, so others are not saying anything, but I expect that you are, if you don't understand, you should tell me. Okay, so okay, but let's keep moving. So we have this, and then from here you see it's completely trivial, right? You similarly write it for this, write for this, multiply them, right? The sides of the triangle that appear in the ratio, they will cancel out, and what you will get is just the usual sine law, right? So what you're going to get is, I mean, just, with the yeah, BD by CD, and so maybe I should have drawn these things again. Can I do that now? Yes. Yes. Okay. So this is the thing, right? So what I was saying is that after the calculations, what you will get is this. You go cyclically, you can understand. So there's hardly anything to remember here. Okay, this is just, that's it. Okay. We also know, so we know that these two things are the same, right? If you have this ratio, you can come to this. If you have this, then you can come to this. Is that right? Right? I mean, those two things are just the same. Those two are always same, right? Like this is, so what I'm trying to make you guys realize is something more fundamental here, right? That even if you did not know this, right? Even if you do not know that it's equal to 1, for example, if the lines are not concurrent, then that's not equal to 1, right? Right? So let's just assume, simply think of it simply, even if that ratio is not equal to 1, we have proved that this is equal to this. That's more fundamental. When this is equal to 1, then, I mean, so if one of them is equal to 1, the other is equal to 1. Okay. We also know, and we are going to maybe use this in some problems I was just thinking of. I mean, I knew them from before, so is that this being equal to 1 also implies that these three lines meet at a point. You see, if that product is equal to 1, it means that the three lines meet at a point. We have not proved it today. I have discussed it earlier, but don't worry about the proof of it. Just maybe know it. Okay. This, as you would expect, these kind of statements. Now let us try to apply this. Let's see if we can apply this. Fine, we are all okay with the statement. Let's look at it. This has many applications in many incidents in Olympiads and so on. It will also have computational applications. You can understand. If the angles are given and you want to check if it's, then you just compute the ratio sine of the angles and you can tell. Let's just say applications. Okay. Let me just say application of Ceva's theorem. That's it. So what should be the first application that we can do? Let us say that I ask you to prove that the angle bisectors are concurrent. Okay. You don't need to apply that angular version. It's up to you. Angle bisectors. This is a very fundamental question, right? That if three angle bisectors, they meet at a point. This picture is again not accurate, but you can. So you understand what we have to show? We have to show that they meet at a point. Okay. There are many ways to do this, but we will try to do it by Ceva's theorem to highlight the application. No, yes, anything? Okay, so since this is the first example, let
Is
us
it
see.
sufficient to say
Yes,
sine alpha by sine alpha into sine beta by sine beta into sine gamma by sine gamma will be equal to 1? That's why they'll be concurrent.
that's all we have to say, right? Correct.
Okay, okay. Yeah.
Oh, what happened to others? Was that like too easy or?
Mhm.
So in this case, this is a by 2, this is a by 2, and so on. So you know that it is 1, right? So see, we need to show, so let's write this clear. We need to show that the angle bisectors are concurrent. Yeah. By the Ceva's theorem, this means that we need to show, so we need to show that sine a by 2 by sine a by 2, because this is what alpha and beta becomes, right? Times sine b by 2 by sine b by 2. But that's true. We know that. That's nothing to do. That's easy. What happened? Hey, it's fine, right? So that's it. Of course, this is, you don't really need this to do this problem, but okay. Right. Let us do another application of Ceva's theorem, which is more interesting, I feel. Okay. First, I will want you people to recall this lemma that we did. This is a standard triangle geometry business. Sorry, I mean circle geometry thing. Is you have a tangent, right? And then you have a chord. Any tangent, any chord, right? And then you try to create a segment out of it. So you join this, name it. Now, one second. The way I have to say this is that you don't really need this. Yeah, that's overkill. Yeah. So angle subtended by chord and tangent. This angle, chord and tangent, is equal to the angle subtended in the opposite segment, right? Which means this angle. Now, why do they just say opposite segment? Because you take any triangle in this segment and you'll get the same angle. So they just say angle of the opposite segment. This is something that we know. Can we just prove this quickly? I'll prove it. This is like a standard theorem that is part of the syllabus of, like, it's part of the school syllabus even. So yeah, how can we prove this? I suppose it will not be difficult. You can draw this line and you know that it is 90 degrees, right? That's because it's tangent. So from the center you draw the line, it is tangent, right? So you just say this theta, this is 90 minus theta, right? Then this is also 90 minus theta. So this is you can do your calculations. It comes out to be 2 theta, right? Because that's isosceles triangle. That's why both are 90 minus theta and it's 2 theta. Then you know that this is half and this theta. There is nothing in that here. That's fine. Okay, so those two angles are same as I was saying, right? These are easy business. Now let us try to see. Now I start with a triangle. Okay. Okay. So again, maybe okay, we are doing this kind of because I have done Ceva's theorem earlier, so maybe you people have not practiced it. So you are not yet comfortable with just applying Ceva's theorem to show something is concurrent. I could see that in the last problem. Okay, but you will be comfortable. Just so we'll do this as an instructive problem. So yeah, but I will expect that you practice. Ceva's theorem, you find problems everywhere. Yeah. So there is this thing. Now I will do something interesting. Okay, I'm going to make a circle, which is so this is ABC. Okay. I'm going to make a circle which is tangent to BC. Okay. And passes through A. Only passes through A. I cannot say anything more, whether it is tangent to AC or not. That I'm not saying. Okay. Okay. So this is tangent. Okay. I'm making this circle. Now I'm going to do this in for all the three vertices. But before that, I have a fundamental question. Can I make more than one such circle? So this is circle, let's call it gamma. Let's just call it C. I've already used. I want to use for the shape, I could have used a different shape of letter. Standard thing. Okay, so gamma, as I've said, what I'm writing is tangent to BC. Okay, and it passes. Is there a unique circle? Yeah.
Yes, sir.
Why?
Sir, only a unique circle can pass through three non-collinear points.
But where is the third point?
Sir, on the triangle only.
On the triangle? This point?
Yes.
But I have not asked that to be fixed, right? So given three non-collinear points and the stipulation that you must pass through those three, I get a unique circle. But I have not stipulated that point. I have only stipulated, you understand, right? B and A, right? So I mean, then you can say, okay, I make this triangle, and I mean, not just I'll say like this. You have this chord, right? And there's just a random line. Now, obviously, through this, with this as the chord, I can certainly draw many circles. Right? My deal was only to pass through those 2 points, But with that, you can make many circles with that hypothesis. Here, the hypothesis is passing through B and A. But obviously, there is slight more that you must be tangent to BC. Right? So just think, okay, why is it unique? So just think, I'll just, I have to change my location, okay? So I'm just think about it, why it is unique. Yes, sorry about the long delay. Yes. So why is it unique? That's a problem on its own, right?
Sir, can we say that there can be only one unique circle drawn such that it's tangential to the side BC, like it needs to be a 90-degree angle?
No, 90-degree angle with what? See, if you only say tangent to
No,
BC,
AB will be the diameter, is it, all the time?
no, AB will not be the diameter. So that is what
Sir,
maybe Aparna is also saying, but I don't, why should AB be the diameter?
no, sir, I meant that it has to be perpendicular from the center. So then, like from
Yeah.
B, then
Mhm.
wouldn't there be only one such point?
I agree that it has to be perpendicular to its center. But why should that be make it unique? You have to use A also, right? If you don't use A, then how will it do? How will you say? You are probably, everybody can probably feel that the A is there and it's needed. Just you have to say it, find a way to say it. It's easy, right? So point is that this length is, let's say, R. This length should also be R, right? And then this point becomes unique, right? So like, forget all this, right? You have this point, right? So you have one point which is fixed, you have another point which is fixed, right? And you are drawing a perpendicular line from here, infinite perpendicular line. So let me not say that the circle is there. Okay. So less than a minute. If it ends, let's join again. Drawing this infinite perpendicular line. Just drawing the line, right? Yeah. What do you need? You need a point on the line so that this length becomes equal to this length. That point is unique. Yeah, because if a point works, if you change the point, then this becomes longer, this becomes shorter. And if you go above, then so there's a unique point where both become equal. And that has to be the center. And so say circle is unique. Center is unique, center is found, and point B on the diameter is found, on the circumference is found. Okay, just clear this up and then just join